I'm going to work problem 434 from Giancoli. It's relatively involved, but it's definitely a problem that we should be able to do. So we have a full Atwood machine with a big mass of 3.2 kilograms, a little mass of 2.2 kilograms, and we know that we are at distance, I'll call it h, which is 1.8 meters above the floor. So what's going to happen is we're going to release this system from rest and let it fall. So our VI is 0, and at the end of this thing it's going to hit the ground with some VF, and this thing is going to be going, well, maybe I should, yeah, I guess I drew this a little bit short here. Alright. That's going to have the same VF, that's important, and this has an acceleration up, which is the same as this one's acceleration down. So, what we're going to look at first is trying to find the acceleration using the forces. So I'm going to look at the forces on little m. There's a tension up and an mg down. That mg is smaller than the tension. I know that because it's accelerating upward. So I'm going to choose up as positive, and my positive direction needs to follow the rope, because if I call this a positive acceleration, I need to call the downward acceleration over here positive. Otherwise my algebra gets all messed up. So my direction of positive follows the rope. The tension up here has to be the same tension because it's the same rope. The mg, however, is bigger, both bigger than little mg and bigger than the tension because it accelerates down. So F net for little m is T minus mg, and by Newton's second law, that equals the mass of little m, because those are forces on little m, times the acceleration of little m. They both have the same acceleration, so we don't need to differentiate. Right, now forces on big M, it's a weight down and a tension up because of our choice of direction of positive. Those are the signs, and that by Newton's second law equals big M times A, because these are the forces on big M. So if we're going to find A, we need to eliminate T. So I'll look at that first equation and add the mg over. And then I'm going to substitute that into the next equation. Now I'm in a good shape. I just have A's and M's and G's. So I'll distribute this negative. And that'll be a minus MA, which I'll add over to the other side. And then factor and divide. And I'll factor on this side too, actually. So I factor out and make this big M plus little m. So that's an expression for my acceleration. Now over here I have my kinematics diagram set up here. And we're interested in how fast it's going at the bottom. We know how fast it's going initially, we know the displacement, and we know now the acceleration. So I'm going to use this. That's 0. 2a delta x, and delta x is h. So that VF when it hits the ground is going to be the square root of, oops, need a bigger square root, 2 times m minus mg, the displacement is h, over big M plus little m, and square root all that business. So now we know that when this top box gets to the top, this is how fast it's moving. And when this big box hits the bottom, and the top box moves up, the rope can't move anymore, so the rope goes slack. So at this point, there's no more tension. Right, after that impact, the rope is not taut anymore, which means there's no tension. So this thing is just in free fall. So what we have is box little m is moving up. It's going to end up with a VF of 0. It's going to have, I'll call this maybe, call this delta y, I guess. Have positive b up. I'm in free fall, so my a is negative g, and my vi here is square root of all that business that's up there. Again, I'm going to use the same model because I know the same information. So VF squared here is VI squared plus 2 A delta Y. My VF is 0. And vi squared is just the square root of that stuff. Plus 2a is negative g. And delta y is, well, just delta y. Alright, so we can simplify a little bit here. I'm going to move, quite a little bit actually. I'm going to move this 2g delta y over to the other side and then get rid of some things. That's an m. Okay. 2's can go, g's can go. So my delta y is m minus m h over m plus m. And that is in addition to that h. So the total height above the ground is just this, which is m minus m over m plus m times h plus h. So I factored out the h here. So if we plug in those numbers, we get that it's 1.19 h, which is 2.13 meters. So fine for the 2.13 meters, but I think it's more interesting the 1.19 h. So what it's saying is that after the big one hits the ground, the little one only goes 20% as high as as that fall distance. So it goes up h, but then it goes up. Oops, it doesn't go up h, does it? It starts h above the ground, and then it goes up h, and then it goes up delta y. So we need to go up 2h. So this is 219. So what I had before there was the displacement. So that's how much it went up. But what it does is ends up 3.94 meters above the ground after having gone upwards 2.13 meters, because it started 1.8 meters off the ground as it was. All right, good. So it's a relatively involved problem, but you definitely need to be able to do each of the individual parts. The important bits here are analyzing the Atwood machine to find the acceleration, getting your directions of positive right, going through the FNets and getting the acceleration, then tying that to the kinematics. The second bit is realizing that you're in free fall after the big one hits the ground because the force situation has changed, and then again it's just kinematics. So a lot of pieces, but you want to look for those connections to put them together.